Hi, my name is Aura, and my project is about optimizing a stent hinge profile given a degradation model. First, we have a quick overview of the presentation. We have a brief introduction. Then we have the procedure, which introduces factors, their corresponding levels, some blocking factors, and disturbances we can encounter. We mention the purpose of the study, the choice of the design, optimization, and some of the expected results. A brief introduction. What's new in STEM technology nowadays? Well, research is focusing on finding the best biodegradable material that best fit the requirements of traditional STEM devices, taking into account their degradation rate and biocompatibility to ensure an optimal performance and lessen the risk of adverse effect of permanent stents. So, given a design that explains the corrosion process of biodegradable stents and how the mechanical properties are changing through time, geometry of the stents, especially hinge profiles, should be taken into account to ensure an optimal performance. So, the purpose of the study is to optimize this stent hinge profile given a degradation model that describes corrosion and how mechanical properties change after a period of time. So, these three are the basic concepts that must be taken into account to develop the degradation model and all the further analysis. First, we have continuum damage mechanics, which is a tool that easily describes the process involved when materials present strain at a macro scale and its corresponding effects. The distributed effects caused by straining lead to material damage, and this damage can be defined as an internal variable related to the loss of mechanical strength of a material. Now, this material can present uniform or pitting corrosion. The distribution of the damage can be uniform or spatially and randomly distributed in all directions, which in this case corresponds to a pitting corrosion. Based on a CDM approach, this damage variable is considered to be scalar and is related to the density of the damage effects on the material. As time increases, the damage variable will increase too until the material will fail. Finally, we have the finite element analysis, which is a method that we use here because it can enable us to predict how a material reacts to physical effects and whether the product will fail or work under certain conditions. To do this, we have to create a mesh in a geometry containing a large number of finite elements. The software uses mathematical equations to predict the behavior of each individual element, so the overall behavior is the sum of all the individual behaviors of each element of the geometry. Now, first we are going to describe the pitting corrosion model. This model assumes that the process of corrosion only takes place on the exposed elements or the elements that are on the surface of the geometry. As we can see here, the elements that are framed are the only ones that can be exposed to corrosion. Next, we define a scalar damage variable as D, which will describe the pitting corrosion behavior through time. D has a damage evolution law defined as we can see in this formula, where Ku is a corrosion kinetic parameter and ΔU and Le are the respective material and Fe model characteristic lengths. For this case, ΔU corresponds to the thickness of the passive film that is created by the corrosion process on the surface of the material, and its value is based on experimental results. Finally, we have this variable, which is lambda-e. It will describe the random and heterogeneous behavior characterized by pitting corrosion. Every surface element on the mesh, which can be represented here, will be assigned a unique random lambda-e value using a Weibull distribution. The probability of the value of lambda-e is determined by the standard Weibull PDF function shown in this formula, where the parameter gamma is the shape parameter that determines the slope of the function and the failure rates. If gamma is less than 1, the failure rate decreases with time. If it is equal to 1, then it is constant, and if it is greater than 1, the failure rate increases with time. Now, when the damage variable increases up to 1 in any surface element of the mesh, then this element is removed, as we can see here. So the surface is then updated, and the neighboring elements of the deleted element will now be assigned a new value of lambda e, following this relationship, where lambda n is the pitting parameter value of the removed element, and beta is a dimensionless parameter that will determine how fast the pits are growing in the material. Finally, the corrosion rate is determined by the rate of mass loss over time based on the average damage value over all of the model elements. Now, each of the values of these variables are based on experimental results and are represented here. Now, we describe the uniform corrosion model. It assumes, as the pitting corrosion model, that only the surface elements will undergo corrosion, and we have also the same damage evolution law. But in this case, the pitting parameter lambda e is set equal to 1. Then we define facets and nodes for each element. The facets are the lines of the element that are directly exposed to the surface, which can be seen here, and the nodes are the corners of each element. Uniform corrosion is simulated by moving these facets along their inward pointing normals at a velocity equal to the corrosion rate that should be determined experimentally. In this case, the product delta U Ku can be replaced with B, which is equivalent to the corrosion rate. Thus, the prediction of these models can be presented in terms of Bt, and it can be considered as a corrosion distance. Now, we are going to present the parameters of the study. The study focuses on a range of sinusoidal stent hinge profiles, as we can see here. We have 6 different dimensions or variables that are going to be studied in this experiment. L1, L2, L3, H1, which will be constant, H2, W, and T. The dimensions are allowed to vary within a specified design space and are reflective of those used in commercial stents. The upper bounds are due to geometrical limitations, and lower bounds correspond to dimensions below which optimal designs are unlikely to be found. Each profile, as I mentioned before, has a fixed height h1 with an outer diameter of 1.5 millimeters. So now the choice of the design is a fractional factorial design. This study has 6 variables, so k equals c. Each one corresponds to a dimension of the stent hinge profile, as we can see in the last image. A full factorial design involves 64 runs of the experiment, but only 6 were done due to cost of computerized simulations. These 6 experiments include the values of the baseline of each variable. Now, following the trade-off table, we have that p equals 3 and we have the following confounding variables: d equals ab, e equals ac, and f equals bc. Now we have that resolution 3 is an appropriate resolution for this experiment because the intention of the experiment is to determine which factors of the dimensions are most important in stent design. Here is a standard table of the experiments that were held. First, we have the first 3 factors, and then we have the other 3 factors that are confounded. D is obtained by multiplying A and B, E obtained by multiplying A and C, and F equals B times C. So now we have that the defining relationship consists on 8 words, since P equals 3. They are the following. We always have the identity, then we have these 3 words, that include the confounding variables ABD, ACE, and BCF, and the other terms are obtained by multiplying these terms between each other. So we have BCDE, ACDF, ABEF, and the last word is obtained by including all the 6 variables of the experiment, A, B, C, D, E, F. Now we show the aliases of each of the main effects of the factors. Since we have a resolution 3 experiments, the main effects are aliased by 2 factors interactions, so we can ignore interactions with a higher order of 3. So we can see that the main effect of A is confounded with B and D and C and E. The main effect of B is confounded with A and D and C and F, and so on. Other factors that can be considered in these experiments are disturbances. Disturbances are uncontrolled and unmeasured variables. As we mentioned earlier, in the pitting corrosion model, lambda E values are generated and are assigned to each of the surface elements of the mesh. These values are unique and randomly generated, so we cannot control which values are going to have each element. So if 2 elements have the same delta lambda E value, the corrosion rate velocity process highly increases. This is a problem because the material fails sooner than predicted and the analysis of mechanical properties cannot be obtained. Then we have covariates that are uncontrolled but measured variables. We made simulations using a AC31 alloy. For this material, we have a given corrosion rate equal to 37.5 micrometers determined experimentally. So corrosion rate depends on the material that is evaluated, so we cannot control it, but we can measure it. If simulations are done with other material, a new value for corrosion rate must be measured to determine the uniform corrosion rate described in the degradation model. Last, we have nuisance factors, which are controllable and measurable variables, but they are not the focus of this experiment. We can recall that the focus of this experiment is to optimize a stent design and to find which geometric feature plays the most important role in corrosion processes. Simulations were run for a AC31 alloy stent. Each alloy has a certain or specific mechanical features, so further experiments may be simulated with other alloys to compare the results. We can block these results or block these factors, since if we use an alloy of AC31 and an alloy of AC30 and an alloy of AC29, we can block these factors to compare the results of each simulation and know if the model is only valid for one material or for several materials. Then we have the optimization process. We chose the RSM because the focus of this study is to optimize a stent hinge profile to ensure a scaffolding performance. The quantity of interest is radial stiffness, which is the slope of the initial portion of the force diameter cube during crushing. We have 6 geometric features that are being evaluated. RSM is a way to explore the effect of each of these features on the outcome, so it would give us information about the most important geometric features to take into account in stent design. The optimization then is focused on maximizing this performance by considering the effects of corrosion. This is achieved by maximizing the radial stiffness after a specific amount of corrosion. Now, we show the steps for optimization. First, we run the first 6 experiments in a random order. For each experiment, a stent geometry is generated. Then, the deployment, corrosion, and crimping simulations are performed for each stent model. We register the results, and then we create a model that best fits these results. We create a Pareto plot, and now we can see which are the most important factors and the insignificant interaction between factors or factors that are involved in this experiment. So the insignificant factors can be deleted from further iterations. We then, in step 6, have to notice the highest value that we obtained in these 6 experiments, because this highest value will correspond to the highest radial stiffness, which is the thing we are looking for. Then further iterations must be done based on this experiment, which has the highest value. So based on these new guidelines, we can increase or decrease lower and upper bounds of each factor. For each iteration, we create a new model and its corresponding contrplot to determine if the model is going towards the steepest path. Finally, we have some expected results. I haven't done myself some simulations, but I found in some article some of the results that are given. For example, we have stent configurations before and after corrosion. These are configurations based on parameterized stent designs. This is the optimized design. We can see that the lumen area is greater in the optimized design and than commercial design. We are interested that the lumen area is greater because this means that the stenosis is lower than in the other case. So this means that the blood flow can fluid constantly and without any disturbance than in this case. Now we have, as we can see, as we mentioned earlier, the radial stiffness. The focus of the study is to optimize or to maximize this value. We can see here that the optimized stent design has a higher radial stiffness and a parameterized stent design. So we can prove that this model can ensure a better stent scaffolding performance. Lastly, we have a graph that can compare the minimum lumen area to the corrosion rate and its mass loss. Recall that mass loss is useful to determine the corrosion rate in pitting corrosion, and the minimum lumen area determines the rate or the grade of stenosis in the artery. So, taking into account the minimum lumen area, we have that the optimized AMS has a higher area than the baseline or commercial AMS, which now can prove that an optimized stent design has a better scaffolding performance. Thank you.